Hi, I'm Karyn, and I'm part of the research team at NWEA. Welcome to RIT 101, an introduction to the scale that sits at the heart of math growth assessments. If you've ever wondered what RIT scores mean, how they're calculated, or why math growth works the way it does, this presentation is for you. We'll cover 4 areas today. First, the purpose of math growth and why that matters. Second, what the RIT scale is and its key properties. Third, how test items get their RIT scores. And finally, how students get their RIT scores through adaptive testing. By the end, you'll understand how all these pieces fit together to create a measurement system that can accurately track student achievement and growth over time. Let's get started. This is the equation that defines the RIT scale, and we're not going to talk about it at all. If that's what you came for, this session might not be for you. Let me emphasize that this is RIT 101, and our goal is to give you a foundational understanding of the RIT scale. We are not going to dive deep into the psychometric formulas, and you shouldn't expect to walk away certified in item response theory. Instead, we're going to focus on the essential concepts you need to know to interpret and apply RIT scores in your work. Before diving into the specifics of the RIT scale, it's important to remember that all good assessment starts with a clear purpose. If we don't know what we're trying to measure or why, we're not going to design a tool that gives us useful information. And that's because purpose drives everything: how we design the test, how we collect the data, and how we interpret the results. But most importantly, how we use them to support student learning. Let me give you a concrete example. Imagine you're measuring height in 2 different situations. First, you are a medical assistant in a pediatrician's office conducting annual wellness visits for children. You need to measure a kid's height to place her on a growth chart relative to population norms for typical growth over time. Doctors collect this information because falling off the growth curve can be an early indicator of health problems. So for this purpose, a precise height measurement is really important. Now, imagine you're a roller coaster operator. Your job is making sure kids are tall enough to ride safely. You're also measuring height, but for you, it's a yes or no question. Do they meet the minimum height requirement for safety? Although height is being measured in both cases, there's a big difference between asking exactly how tall are you and are you tall enough? The purpose behind the measurement determines the level of precision and accuracy that's required. Here's another reason purpose matters. Validity is inherently tied to purpose. A test isn't just valid in general, it's valid for something. Measures are validated for specific uses, and when we use them for something else, that validity doesn't automatically carry over. To stretch our height example, imagine my kid's pediatrician skips the height measurement altogether and just jots down, tall enough to ride all the rides at the fair. Is that useful for monitoring growth or spotting health concerns? Nope. Same measurement, different purpose, completely different implications for what the data can be used for. Hopefully, I've started to paint a clear picture of why the purpose of an assessment matters, and that using the right tool for the job is everything. With that understanding, let's shift gears and get into map growth specifically. The purpose of map growth is simple but powerful, and that is to precisely and accurately determine a student's achievement and track their growth over time. And that purpose drives every design decision behind the test, from how it adapts, to how items are calibrated, to how the RIT scale itself is built. Let's think about what it means to precisely and accurately measure achievement. Consider a group of 3rd graders. These students may be in the same grade, but they're naturally going to differ in their math achievement levels. Some are above grade level standards for math, some are nearing that standard, and some are well below. Now imagine that we were only interested in assessing whether students meet the grade level standard, as many summative assessments are designed to do. In this case, we would focus on a narrow band of math achievement, just above and below that standard. While this approach provides accurate information about students performing within that specific range, it offers limited insights for those who are significantly above or below that standard. Since the purpose of map growth is to precisely measure a student's achievement, it would be counterproductive to focus solely on a narrow band of achievement near the grade level standard. Instead, we need to be able to capture achievement regardless of whether their performance is above or below grade level. In other words, we want the assessment to have a very high ceiling and a very low floor. This allows us to capture the full range of student abilities, providing valuable insights for both struggling students and those who are excelling beyond their grade level. Tracking back to our discussion of how different purposes for measuring height lead to different types of data and levels of precision, homing in on grade level standards is akin to asking a dichotomous yes-no question. Does the student know enough math to meet the grade standards? This approach focuses on that narrow band of achievement. And this is the key difference. Instead of asking, do you meet the standard, a yes-no question, Map Growth asks, how much do you know? And this requires meeting students wherever they are. Being able to do this, meet students where they're at, regardless of grade level, and still accurately and precisely measure their achievement, is all made possible by the RIT scale. We've established why purpose matters for any assessment and identified Map Growth's specific purpose, to precisely and accurately measure student achievement and growth over time. Now the question becomes, how is this actually possible? What makes Map Growth different from other tests you might be familiar with? The answer lies in the RIT scale and its unique properties. Let's dive into what makes this scale so powerful for measuring growth. The scale that underlies Map Growth is developed using item response theory, or IRT, which is a psychometric approach to measurement. Among the various IRT models out there, we specifically use the RASH model, which is why we refer to the scale as the RIT scale. Let me reassure you again that you don't need to be a psychometrician to understand this presentation, and we won't delve deeply into the technical details. Here's the one thing I want you to understand about IRT. It recognizes that a test response isn't just about the test taker or just about the item. It's about the interaction between the two. Think of it like rock climbing. Whether or not you can complete an ascent at the climbing gym depends on two things: your skill level and the difficulty of the route. A beginner might struggle on an intermediate wall, while an expert walks right up it. To predict whether a climber can scale a wall, you need to consider both the person and the challenge. Now let's apply that idea to an achievement test. The probability a student answers a question correctly depends on the student's math achievement and the difficulty of that particular item. A high-achieving student is more likely to answer items correctly than a low-achieving one. And a math item that is very difficult, say, what's the square root of 983, is less likely to be answered correctly than a very easy item, say, what is 2 plus 2? So why does this matter? Well, it depends on the purpose of the assessment. If your goal is to check whether your students have memorized their multiplication facts, you don't need IRT. You give every student the same quiz and score how many they got right. That's a fixed form mastery test. But Map Growth is different. Its purpose is to meet students where they're at, to find the exact right challenge level so we can measure their growth over time. That kind of precision isn't possible with a one-size-fits-all test. It requires the test to adapt in real time, and that's only possible with IRT. IRT gives us one continuous scale. In the case of MAP, that's the RIT scale. It's the same scale we use to locate both how hard a question is and how high a student is performing. For students, a RIT score represents their current achievement level in a subject, how advanced their knowledge or skills are. For items, the RIT scale is a measurement of item difficulty. Higher numbers on the scale indicate more difficult items. Let's get a little bit more concrete about what this means. Imagine this number line represents the RIT scale, and let's pick a particular point on the scale, say 200. How would we interpret a score of 200 for a student? Well, a 200 RIT score for a student tells us that this student gets 50% of items at this difficulty level correct. And how would we interpret a score of 200 for an item? Well, a 200 RIT score for an item tells us this specific item is answered correctly by 50% of students at this achievement level. If you're used to thinking about tests as tools for measuring mastery, it might feel strange that Map Growth, and item response theory more broadly, hinges on students getting about 50% of the items correct. So why does that make sense? Well, imagine I gave a set of very basic arithmetic items to a group of 4th graders. They would likely get all these items correct because these items are too easy for their level. So next, I give them a much harder set of items. But now no one gets any right because these are too hard. What have we learned about these 4th graders from these two sets of items? Not much, except for that I am bad at picking items. If a student gets 100% of items correct, we know that they have mastered those skills, but we don't know what more they could do. Conversely, if students get 0% of items correct, we know the content is too challenging, but we don't learn much else about their abilities. The sweet spot is right in the middle. We learn the most about students when we identify the edge of their ability, the point at which they are getting about half of items correct. That 50% point gives us the clearest signal of what they know and what they're ready to learn next. This is why it's problematic to think of Map Growth as a mastery test. Map Growth is not a mastery test. It's a measurement tool, and it's designed for students to get around half the items wrong. Not because students are failing, but because that's where the most useful information lives. MAP growth scores are reported on the RIT scale, an equal interval, vertical scale that is continuous across grades, and stable over time. Let's unpack that. The RIT scale is an equal interval scale. That means a 10-point difference on the scale means the same thing, no matter where a student falls. The distance between 200 and 210 represents the same growth as the distance between 250 and 260. Think about it like a ruler. 1 inch is 1 inch, whether you're measuring a kindergartner or a pro basketball player. That's what makes it meaningful. We can track change accurately and consistently. Why does this matter in schools? Because it allows us to track progress within and across grades without needing to redefine what a score gain means each time. To illustrate this, let's consider a case where the scale is not equal interval. Percentiles are an example of a non-equal interval scale. This table shows you household income percentiles and their associated annual income levels. A 5 percentile point difference has a very different meaning depending on whether you're at the low or high end of the distribution. This variability makes percentiles less useful for certain types of comparisons. Being able to understand what a 5 percentile point difference means depends on where you are in the distribution. Near the lower end of the scale might mean a difference of a few $1,000s, while near the upper end, the difference is tens of thousands of dollars. In contrast, an equal interval scale like the RIT scale ensures that a unit increase means the same thing across the entire range. And this is a key part of what makes the RIT scale a strong tool for growth measurement. It tells us how much students have progressed, clearly and consistently, no matter where they start. The next key property to keep in mind is that the RIT scale is a vertical scale. This simply means that we use the same scale to measure students regardless of their grade or their ability level. This is really critical to the purpose of MAP growth, to measure achievement precisely and accurately. If we look at the typical makeup of a 5th grade class, for example, you'll see a really wide range of abilities. Some estimates suggesting only about a quarter of students are actually at grade level, and the rest are above or below, sometimes well above or well below. We want MAP growth to meet students where they're at, so the scale cannot be tied to a particular grade level. We want the floor to be very low and the ceiling to be very high, so we can capture the full range of achievement levels. The vertical scale also makes it possible to measure growth over time. With non-vertical scales, growth determinations are more challenging. For instance, if we compared this student's end-of-course grades, what could we conclude about her growth in math over time? Does going from an A in 4th grade to a C in 6th grade indicate she's losing math skills? No. Change over time cannot be evaluated comparing grades because they are a non-vertical scale. In contrast, the RIT scale provides a continuous, stable measure that allows us to track a student's academic progress accurately over time, offering a clear picture of their growth. Finally, the RIT scale is stable over time. This means that the interpretation of the scale remains consistent over the years. For instance, a RIT score of 220 has the same meaning today as it did 5 years ago. The stability doesn't happen by accident. As we'll discuss later, we continuously monitor the scale to ensure its stability and make adjustments as necessary. To illustrate why this is important, let's consider a case where an underlying scale is not stable over time. Have you heard of vanity sizing? Well, clothing brands figured out that shoppers feel better and spend more when they fit into a smaller size. So over time, they have quietly shifted what the numbers mean. Back in 1970, a 26-inch waist might have been labeled a size 12. Today, that same waist might be a size 0. The body didn't change, the scale did. That's what happens when a scale isn't stable over time. You can't compare sizes from one decade to the next. And anyone who's ever tried to squeeze into that pair of vintage jeans knows this firsthand. Imagine if test scores worked that way. Keeping the RIT scale stable makes it possible to track real growth over time and to compare cohorts year to year. When the scale stays stable, we can be more confident that any progress or declines that we see are real and not an artifact of the measurement scale. So far, we've established that MAP growth exists to precisely measure student achievement and growth. And we've explored the key properties of the RIT scale that make this possible. It's equal interval, vertical, and stable over time. Now I want to shift from the what to the how. How does this actually work in practice? How do test items get their RIT scores in the first place? This is where we move from theory into the real process that NWEA uses to build and maintain the item bank that powers MAP growth. To understand how an item gets a RIT score, let's walk through the item calibration cycle using this new math item as our example. You can see it's asking students about dividing apples equally among friends, a fairly straightforward division problem. But here's the thing. Before this item can become part of our item bank and appear on student tests, it needs a RIT score. Remember, the RIT score reflects the item's difficulty, specifically the achievement level where 50% of students would answer it correctly. So how do we figure that out? Well, let's follow this item through each step of the calibration process. The first step is for our content specialists to assign a provisional RIT score. Now, I like to joke that this involves a highly technical process called humans making their best guess. But in reality, these aren't just any humans. Our content specialists have deep expertise in both the subject matter and state standards. So they look at an item and consider, what mathematical concepts does it require? What grade level typically learns these skills? How might students approach this problem? Then based on their expertise, they make an initial estimate of where this item will likely fall on the RIT scale. This gives us a starting point, but it's just the beginning. Our content specialist's best guess of an item's difficulty isn't enough. We need to empirically determine how difficult that item is. To do this, we need data from test takers, which is where field testing comes in. Here's what you should know about the field test process. Every student is going to see between 1 to 3 field test items per test. Obviously, those items don't count towards their score. It's also a seamless process for students. We don't point out, for instance, that these are field test items because we don't want them to withdraw effort. And in the field test process, each new item is administered to at least 1,000 students. The purpose of field testing is to calibrate the difficulty estimate of each new item. We embed new items in the assessment alongside the items that will actually be used to determine a student's score. This method allows us to link new items to the existing item bank. By comparing how new items perform alongside items that have already been calibrated, we can accurately determine the actual difficulty of each new item. This is an item response function plot. It shows the probability of a correct response to an item against the achievement levels of the students who responded to that item. Let's look at a point right on the curve, students with a RIT score of 180. About 10% of these students got this item right. This item is too difficult for these students. As we move to the right of the curve, you'll see that the probability of correct responses increases. The question becomes, at what achievement level do half of the students get this item correct? That's the key. An item's difficulty is defined as the RIT score where 50% of students answer it correctly. In this case, that point is right here, a RIT of 200. Once we field test an item, we look at how well it performs compared to the theoretical model. That's what these IRF plots help us evaluate. Here is an example of an item with good fit. The actual student performance closely follows that expected S-shaped curve. In other words, lower achieving students rarely get it right, and higher achieving students usually do, just like we'd expect. That tells us this item behaves predictably. We can use this data to fine-tune the item's difficulty, adjusting the provisional estimate to reflect the observed RIT where 50% of students got it correct. Now take a look at this item. Something is off. Students at both low and high achievement levels are getting it correct at about the same rate. That flat, unpredictable pattern tells us this item isn't doing its job. It's not distinguishing between students with different levels of achievement, and that's a problem. When we see this kind of misfit, we know the item likely needs to be revised or removed from the item bank altogether. If the item is not successfully calibrated, it's returned to content specialists for review and editing, and then re-entered into the field test process. If an item is successfully calibrated, it's added to the item bank. The item bank includes over 40,000 items, and items are continually being added. Items are also regularly being retired as standards change, or removed if they're determined to be problematic. Remember, when we talk about the properties of the RIT scale, we mentioned that it's stable over time. This stability doesn't happen by accident, and we continually monitor items across the entire item bank to maintain the continuity of the RIT scale. Part of this routine monitoring includes regular reviews of items to check for parameter drift. Parameter drift occurs when an item becomes easier or more difficult over time. In most cases, item difficulty remains highly stable, as you can see in this graph. However, there are times when scale maintenance is needed to adjust item calibrations and ensure ongoing stability. For instance, in 2020, we adjusted the items in the K2 test to address parameter drift between the K2 test and the 2.5 test. We've just walked through the rigorous process of how items get their RIT scores, from content specialist estimates through field testing and calibration. Every item in our bank of over 40,000 items has gone through this process to determine its exact difficulty level. Now let's flip to the student perspective. We have all these carefully calibrated items with known RIT difficulties. The question becomes, how does MapGrowth use these items to determine where each individual student falls on that same RIT scale? This is where the magic of computer adaptive testing comes in. Earlier, we talked about how MapGrowth is designed to meet students where they're at. Now, that's not just a nice idea, it's a key part of how the test works. And making that possible requires a very different kind of assessment, a computer adaptive test, or CAT. It's the engine that allows us to tailor the test to each student's achievement level in real time. Let's talk about what that actually means, how it works in practice, and why it's such an efficient and powerful way to pinpoint each student's achievement level. Let's walk through what this looks like in action. As you already know, MapGrowth doesn't just give every student the same set of questions. It adjusts in real time based on each student's performance. The difficulty of the first question is set according to what we know about the student based on their prior test history, or if that's not available, the average RIT score for the student's grade. Now, if the student gets it right, what should the test do next? Should the next item be harder or easier? Exactly, it needs to get harder. There would not be much to learn by giving the student an easier item. The student got the question right again, so the test adjusts up again. Okay, now imagine if the student gets the next item wrong. We don't keep climbing, now we adjust down. So notice that the size of adjustments change as we move through the test. It starts with a provisional estimate, then makes larger jumps early on, getting easier or harder based on a student's answers. Then once it starts to home in on the right level, it makes smaller, more targeted adjustments before ultimately settling on that student's RIT score. Take a look at the curve here. After just 7 or 8 items, the test already has a pretty good sense of where the student lands. This means your student isn't wasting time on test questions that are either too easy or way too hard. And this is where the CAT is more efficient than a fixed form test. This kind of precision would take far more time on a fixed form test. But because MapGrowth is adaptive, we reach that level of precision with fewer items. MapGrowth can go up to 40 items. And we set that 40 item max because our research shows that's about the number of items required to reach an acceptable level of precision. Our measure of precision is the standard error of measurement. Notice that's now layered onto the graph for each item. The SEM tells us how confident we are in the student's score. Think of it like a margin of error in a poll. Smaller is better. What do you notice about how the SEMs vary across the length of the test? Well, we learn more with each item, so SEMs decrease and precision increases. Once the SEM gets low enough, the test is confident in the score, even if we haven't had to administer the max of 40 items. So why is a lower SEM better? Well, consider these two graphs. Both students you see here have identical RIT scores, 214 in the fall, 218 in the winter, and 222 in the spring. So comparing RIT scores, they've shown the same growth. But for the student on the left, the SEM is smaller. That means we can be much more confident that the growth we're seeing is real. There's no overlap between the fall and spring scores, so it's highly unlikely this change is just noise. Now look at the student on the right. Here the SEMs are much wider. That fall score of 214, it could plausibly be as high as 222, and vice versa. That spring score of 222 could plausibly be as low as 214. In other words, we can't rule out that this student's scores haven't changed at all. This is why score precision matters so much. So far, we've walked through how MapGrowth adapts based on student performance, getting easier or harder depending on how a student answers. But I've actually oversimplified things a bit. Item difficulty is a big part of the story, but it's not the only factor that determines which items a student sees. Let's talk about the other factors. The item selection process is guided by something called test blueprints. Essentially, the blueprint sets the rules for how the item selection algorithm picks the right items for each student. Over the past several years, we've been updating the blueprints behind the testing algorithm that guides item selection for students. To understand what's changing, let's first look back at how item selection worked in legacy MapGrowth. The algorithm followed 3 core blueprint rules. The first, regarding longitudinal constraints. A student shouldn't see the same item again too soon, usually not within 14 months. Second, instructional area coverage. Items are selected to evenly represent the different content areas within a subject. And finally, appropriate difficulty. Items are chosen based on the student's achievement level, as we saw in the CAT demo. Map Growth now uses an Enhanced Item Selection Algorithm, or EISA for short. With EISA, those 3 rules still matter, but there are 2 key enhancements. First, instructional area weighting is now flexible in math. Instead of equal representation, the blueprint can reflect state standards, so students may get more items from some instructional areas than others, depending on what's emphasized in their grade and your state. Second, EISA introduces a new rule, and that is it prefers grade level items. When possible, the test prioritizes questions that match a student's enrolled grade. This helps ensure that the test results are more instructionally relevant. Importantly, though, the test is still adaptive and will select an off-grade item if that's the most suitable one for that student. So that's how the blueprint guides what students see on the test. And with EISA, that guidance is getting smarter, more tailored to grade level expectations and state standards, but without losing what makes Map Growth unique. Now that we've covered the full picture, let's step back and pull it all together. We've covered a lot today, from what the RIT scale is and how it works, to how students and test items get their RIT scores, to what's changing with EISA. Here's what I hope you'll take away. First, Map Growth is fundamentally different from mastery tests. It's designed to meet students exactly where they are, whether that's above, below, or right at grade level. The goal isn't to gauge students' proficiency to particular grade standards, but to precisely measure their current achievement and track their growth over time. Second, the RIT scale makes this possible through its unique properties. Because it's equal interval, vertical, and stable over time, we can trust the growth it shows us and make meaningful comparisons across students, grades, and years. Third, there's tremendous rigor behind every RIT score. Each item goes through extensive field testing and calibration. The adaptive algorithm makes thousands of decisions to find the just right question for each student. None of this happens by accident. Finally, students get their RIT scores through MapGrowth's adaptive testing approach. Because the test adapts in real time, no 2 students will ever have the same test experience. The algorithm is working behind the scenes to select the right item for each student based on their grade level, state standards, and their performance in that moment. This personalized approach is what allows us to pinpoint each student's achievement level so precisely. Understanding these foundations should give you greater confidence in interpreting Map Growth data. When you see a RIT score, you now know it represents a student's position on a carefully constructed, scientifically sound measurement scale. I hope this overview has been helpful. This video is part of a series exploring Map Growth in depth. I encourage you to check out related videos that dive deeper into test design and our norms. Thanks so much for watching.